In this video, we'll be looking at how we can evaluate the limits of expressions that have trigonometric functions. And we will be using a specific and important limit when it comes to calculus, which is that the limit as x approaches 0 of sine of x divided by x is 1. And so this limit is very important because when we have trigonometric expressions and we want to determine their limits, we can use this limit over here to try to get rid of the trigonometric expressions to further simplify our problem and hence evaluate limits. I think it's important to start from a specific example to then induce a general method for solving trigonometric expressions. So here we have a fraction of two functions. Here we have x minus 1 squared divided by sine squared of 4x minus 4. And what we notice is that the limit as x tends towards 1 of x minus 1 squared is 0. And same thing for sine squared of 4x minus 4, because 4x minus 4 tends towards 0, and the limit of sine of x as x tends towards 0 is 0. And hence, we have a limit of the form 0 over 0. And what does this mean? Well, it means that we cannot evaluate this limit the way it is. We have to algebraically manipulate it and find some clever ways to adjust our expression in order to calculate the limit. And the way we do that is by using this limit over here. In fact, this limit will help us because sine of x divided by x as x tends towards 0 is 1, and hence we get rid of the sine of x here. And so this is what we want to do in this example over here. We want to get rid of the sine squared of x in order to evaluate the limit. One thing I want to emphasize on is the fact that here x tends towards 0, and therefore whatever is in the input of the sine function has to tend towards 0. In this case, we have that because 4x minus 4 tends towards 0 as x approaches 1, because 4 minus 4 is equal to 0, and hence we can use this limit. In this video, I'll be using two methods to evaluate this limit, and in the next video, we'll be looking at a harder example where we need to use the sine of x over x limit. But before I start solving this problem, I want to talk about the fact that since sine of x over x tends towards 1 as x tends towards 0, we reciprocally have that the limit as x tends towards 0 of x over sine of x is also equal to 1. We just take the reciprocal here in order to have this limit. And the reason we can do this is because x is never equal to 0, but its limit is 0. Its limit, the limit has this notion of neighborhood, so a local property, and not a punctual property. So x is never actually equal to 0, which is why we can take the reciprocal. So now for this example, what I want to have is something of this form, and therefore I need to multiply by 4x minus 4 on the top and on the bottom in order to have something of this form. However, we see here that we have sine squared and not just sine. So we have sine of 4x minus 4 times sine of 4x minus 4. So I need to have 4x minus 4, the whole thing squared. So let me repeat this by writing it down. So we have the limit as x tends towards 1 of x minus 1 squared times 4x minus 4 divided by sine squared 4x minus 4. But since we multiply by 4x minus 4, we need to divide by 4x minus 4. So we multiply by 1 over 4x minus 4. So we have something of the form big X divided by sine of big X, which in this case big X is 4x minus 4. But since we have sine squared, we have sine times sine. So we need to have big X times big X. And so we need 4x minus 4, but twice, so squared. And since we multiply by 4x minus 4 squared, we need to divide by 4x minus 4 squared. In other words, this part of the expression over here is actually equivalent to big X squared divided by sine squared of big X, which as big X tends towards 0 is this tends towards 1. And big X tends towards 0 because remember, small x tends towards 1 and 4x minus 4 therefore tends towards 0. And hence big X tends towards 0. And so we can use this limit over here to solve this. So I've written down what I just said over here. And what's great about using this limit is that now we have considerably simplified our problem. Indeed, now we just have the limit as small x tends towards 1 of x minus 1 squared divided by 4x minus 4 squared. So now we have a fraction of two polynomials, one on top and one on the bottom. And we know that the limit will be associated with the highest order of x. In other words, we don't need to distribute this whole expression over here. We just need the highest order term, which is x squared plus something we're not interested in, divided by 4x, the whole thing squared, plus something we're not interested in. I've written it down in a more acceptable way. And so if we simplify the x squares, we get that the limit of this complicated expression over here is just 1 over 16. And so this is our answer. So to quickly sum up, since we couldn't evaluate this limit as it was because it's 0 divided by 0 essentially, we tried to manipulate this expression to get something of the form sine of x over x or x divided by sine of x. And we know that this limit is equal to 1. And so that is what we did over here. And so we considerably simplified our expression here because this limit is 1. And so we get a much neater limit, which is 1 over 16. Now the problem with the method that I just used is that multiplying by 4x minus 4 on both on the top and on the bottom can be quite messy sometimes, and sometimes it might make the problem more complicated. And so now I will use another method which is longer but easier to understand. So first we can notice that we can factorize 4x minus 4 by 4 times x minus 1. And so I'll write that down. And now to make this expression neater, we can use a change of variable. Though it's not a necessary thing to do. We don't need to use a change of variable, but I'll use it just to make the expression neater. So I'll set y is equal to x minus 1. And so this considerably simplifies our problem because now we have the limit of y tending towards what number? Well, the limit of x is 1. So the limit of y will be 0 because 1 minus 1 is 0. And that is what we need to use this limit over here because we want something that tends towards 0. And that is what we have. We have y tending towards 0. And so we have y squared divided by sine squared of 4y. Now, just like in the previous method, we need a 4y on the top to use this limit over here, or this one in this case. So we multiply on top and on the bottom by 4y, so we have the limit as y tends towards 0 of y squared times 4y divided by sine squared of 4y times 1 over 4y. But remember, since we have sine squared and not just a simple sine, we need 2 of the 4y, so 4y times 4y, in other words, 4y squared. And this simplifies our problem because now we can use the x over sine x limit, which is 1. And so this is actually 1 when y tends towards 0. And the reason for that is even though here we don't have, we have 4y and not just y, we can set big X is equal to 4y. And the limit of big X as y tends towards 0 is also 0. So we essentially have big X squared divided by sine squared of big X, and it will tend towards 1. So thanks to that limit, we now only have the limit of y tending towards 0 of y squared divided by 16y squared, because 4 squared is 16, and so this is equal to 1 over 16. So essentially, this method consists of using a change of variables in such a way that the new variable tends towards 0, which is required in order to use this limit, remember. And thanks to this change of variable, we try to manipulate and change our expression in order to get something of the form x over sine x in this example, or general sine x over x, in order to simplify our problem and obtain our limit.